the RLC circuit has different damping regimes. Its behavior depends on how much damping there is. So one is called light damping, or under damping is another name for it. It occurs when R is much less than 2L. From the solution, which I'll write again, Q equals Q initial e to the minus R over 2L T cosine, oh my gosh, the square root of 1 over LC minus R over 2L squared T. Okay. So from this, you can see that the quantity R over 2L is pretty important, right? It's what's telling you how much damping there is here, how much the omega is reduced here. So in underdamping, R is much smaller than 2L. If that's the case, this is a very small number. This is like 0. This is a very small number. So basically, this is approximately e to the 0, which is 1. So it doesn't damp. And here, again, R over 2L is a small number. If you square it, it's a really small number. So this is approximately 0. And in that case, the circuit would oscillate at the undamped frequency, the square root of 1 over LC. It would oscillate as though the resistor weren't even there, if it were just an inductor and a capacitor. So if you wanted to plot this, I won't plot it in detail, but you can see what it would do is it would just oscillate. Cosine forever. The damping is essentially gone. So when we usually think of an oscillating RLC circuit, this is what we're thinking about, a really small amount of resistance that we can maybe even ignore. There's also, other end of the spectrum, there is overdamp. So overdamped is a special thing that happens as soon as R becomes greater than the square root of 4L over C. Okay? And by these C's, we mean the capacitance. There's no more parameter C. And you can see what would happen. Let's see, if you were to plug that in, if R was going to go here, we'd have Q, that's fine, would be Q init, that's fine. E to the minus, oh, let's see, if this were the square root of 4 over LC, well, I didn't mean to do this. Let's see, R, this would be over 2L, the square root of 4L over C, and then divide that by a 2L, which would come in as a 4L squared. And then, I don't know, it'd be 1 over LC times time. So it'd still be damped by some amount. But then let's look at this cosine term. The square root of 1 over LC minus, and then if we made R squared here, this would be R squared over 4L squared. Well, if R squared is 4L over C, and then over 4L squared, that becomes, cancel, 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 it becomes minus 1 over LC. It's 1 over LC minus 1 over LC. Basically, it becomes so damped, the frequency is driven to 0, and it doesn't oscillate anymore. If R is greater than this number, this term becomes negative. This gets even bigger. You have the square root of a negative number. Then the frequency is imaginary, and it doesn't oscillate anymore. So in the case of overdamping, it doesn't oscillate at all. It actually does something like this. It starts up here, and it goes, and it actually never reaches 0, or it never crosses over. Just goes off forever towards infinity, and it never crosses over. If it's undamped enough, if the damping is low enough to cross over, then it's technically going to oscillate. But at this value and above, it basically never gets there. And really, to get the accurate solution, you shouldn't have made this guess. You have to make a different guess to the equation to get the right answer when you are overdamped. So there can be many behaviors depending on the relative values. There's not only one answer to the differential equation that describes the charge motion. It depends on the parameters.